Stop. Look at your hand. Right now you feel time pushing you forward from the past into the future. It feels like a river, right? A relentless current dragging you towards tomorrow. You get older, coffee gets cold, memories fade. It feels absolute. But here is the thing nobody tells you. If you zoom in, past your skin, past the cells, down to the particles of light and matter that build your reality, that river stops. In the fundamental laws of physics, there is no arrow of time. None. The equations work exactly the same way backwards as they do forwards. So why do you remember the past but not the future? There is a secret hidden in the math of light itself, a secret that suggests antimatter, that exotic sci-fi stuff, isn't just rare explosive dust. It might be something far stranger. It might be light, moving backwards in time. Imagine that. Half the universe might be traveling in the wrong direction, and you're just caught in the middle. Sound impossible? A paradox? Wait until I show you the diagrams. Because once you see how light actually moves, you'll never trust the clock again. Let me show you. Let's start with a simple experiment. You can do this in your head. I want you to imagine dropping a pristine ceramic mug on a concrete floor. Smash! Shards fly everywhere. Tiny white fragments slide under the fridge. Hot coffee splashes onto your socks. It's a mess. Now, hit the rewind button. Imagine the coffee leaping off your socks, gathering into a liquid ball. The shards slide out from under the fridge, jump into the air, fuse perfectly together, and land softly in your hand. You know immediately that the second version is fake. It feels wrong. It violates your common sense. In your world, things break. They don't unbreak. This one-way street sensation is what we call the arrow of time. But here's the part that keeps physicists up at night. If you look at the fundamental laws that govern the atoms in that mug, I'm talking about the deep, hard math of the universe. That arrow doesn't exist. It's not there. Look at Isaac Newton. Look at Einstein. Look at Schrödinger. In almost every single master equation of physics, time is just a label, a variable, t. And the terrifying thing about t, you can make it negative. You can swap t for t, and the equation still works. Do this right now. Imagine a single atom hitting another atom, like two billiard balls colliding on a pool table. Clack, they bounce off. If I recorded that collision and played it backward for you, could you tell me which version was real? No, you couldn't. A backward collision looks exactly the same as a forward collision. So here is the paradox. Your life is made of atoms, and atoms don't care about time. They can go forward, backward, sideways. It's all valid math to them. So if the building blocks of reality don't have an arrow of time, why do you? Why can't you remember next Tuesday? Why can't you unstir the milk from your coffee? People say, oh, that's just entropy. Disorder increases. Stop. That's a lazy answer. Entropy explains the mug breaking. It explains the mess. But it doesn't explain what happens when you look deeper. Because when you force light and matter to dance together, the math starts to suggest something much crazier than just disorder. It suggests that forward might just be a perspective. And if you want to understand why, we have to look at the one place where time actually breaks. Let's zoom in. We are leaving the kitchen floor. We are going way down, past the ceramic shards, past the molecules, into the quantum realm. Down here, things get symmetrical. In physics, we have a sacred rule called CPT symmetry. Sounds like jargon, but it's actually beautiful. It stands for charge, parity, and time. Think of it like a three-way mirror for the universe. C is charge, swap positive for negative. P is parity, swap left for right, like a mirror. T is time, run the clock backward. The rule says, if you flip all three of these at once, the universe should look exactly the same. The laws of physics must hold up. It's like the ultimate undo button that restores balance. But wait, what happens if we just flip T, just time? For a long time we thought, yeah, sure, time is just a coordinate, who cares? But then we looked at light. Light is weird. It's not just a wave, and it's not just a particle. It's a photon, a massless packet of pure electromagnetic energy. And light connects everything. When you see a star, a photon hit your eye. When you turn on a lamp, photons flood the room. Here is a trap. If you take a video of a planet orbiting the sun and play it backward, it's still a planet orbiting a sun. Gravity doesn't care. It's symmetric. But if you take a video of an electron emitting a photon and you play that backward, what do you see? You see a photon going into an electron. You see absorption. Emission becomes absorption. The process reverses perfectly. So if light can travel from A to B, the math says it must be equally possible for it to travel from B to A, backwards in time. Hold on, did you catch that? I'm not saying light turns around and flies back. I'm saying the process itself is time reversible. This implies something massive. It implies that at the fundamental level of reality, cause and effect might be interchangeable. Did the electron spit out the light? Or did the future electron swallow the light from the past? In the math, it's hard to tell the difference. And this ambiguity, this symmetry trap, is exactly where Paul Dirac stumbled upon a ghost in the machine that changed everything. Let's talk about Paul Dirac. Picture a man so quiet that his colleagues at Cambridge invented a unit called the Dirac, 1 word per hour. That's how much he spoke. He didn't care for philosophy. He cared for beauty in equations. It's 1928. He's trying to combine quantum mechanics, the rules for tiny stuff, with relativity, the rules for fast stuff. He writes down an equation for the electron, and it's perfect. It describes spin, magnetism, everything, a masterpiece. But there is a problem, a big, ugly problem. You see, when you solve an equation like x2 equal to 4, you get 2 answers, x equal to 2 and x equal to minus 2. Both are mathematically true. Dirac's equation was like that. It had 2 solutions for energy. One solution described the electron we know, moving forward in time with positive energy, normal stuff. The second solution, it described an electron with negative energy. What on earth is negative energy? It's not just having 0 energy, it's less than nothing. It's like having minus $50 in your bank account, but for the universe. Most physicists at the time said, ignore it. It's just math junk. Throw it away. But Dirac couldn't. He looked at the math and said, no, the math is smarter than we are. He realized something profound. If this negative energy, quote, electron exists, what would it look like to us? Well, it would have the same mass as an electron, but it would have the opposite electric charge. Instead of negative, it would be positive. And here is the kicker. If it had negative energy, it would behave as if it were moving backward in time. Think about that. A negative energy particle moving backward in time looks mathematically identical to a positive energy particle moving forward in time, but with the opposite charge. Let me say that again. An electron moving backwards in time looks exactly like a positron, anti-electron, moving forwards in time. This was the birth of antimatter. Dirac predicted it purely from math. 4 years later, Carl Anderson found it in a cloud chamber, a particle that curved the wrong way in a magnetic field. Everyone cheered, we found antimatter. But they missed the point. They thought they found a new particle. But what if they just found the same particle doing a U-turn in the 4th dimension? This is where Richard Feynman enters the chat. And he didn't just accept this idea, he drew a picture of it. A picture that changed how we see reality forever. Enter Richard Feynman. If Dirac was the silent genius, Feynman was the loud one. He played bongos, he picked locks, he explained physics with strippers in bars. He hated confusing math, he wanted to see it. So he started drawing. He drew lines, squiggles, arrows. These became known as Feynman diagrams. Today, they are the hieroglyphics of modern physics. Every particle physicist uses them. But let's look at one, just one. Imagine a simple interaction. An electron meets another electron. They repel each other because they have the same charge, like magnets pushing apart. In a Feynman diagram, you draw time going up the page, or to the right, it doesn't matter. Let's say up. You draw two straight lines coming in from the bottom. Those are the two electrons. Then they get close. They exchange a photon, a squiggly line connecting them. Zip! That photon carries the force. Then the two lines bounce apart and go off to the top of the page. Simple. But Feynman noticed something weird in his own drawings. What if one of those lines pointed down? What if an arrow on the line pointed backward against the flow of time? Mathematically, a particle moving backward in time with negative energy is indistinguishable from an antiparticle moving forward in time with positive energy. We just covered that with Dirac. But Feynman made it visual. He realized, wait, if I draw an electron going backward in time, it looks exactly like a positron going forward. So in his diagrams, he made a rule. Rule: arrows pointing forward in time represent matter, electrons. Rule: arrows pointing backward in time represent antimatter, positrons. This wasn't just a shorthand, it was a revelation. It meant that every time you see antimatter in an equation, you can mathematically treat it as normal matter traveling back into the past. Think about a positron meeting an electron. They annihilate. Boom! Pure energy. Two photons fly out. In a Feynman diagram, this looks like an electron moving forward in time, hitting a photon, and suddenly turning around to go backward in time. The positron is just the electron after the U-turn. It's the same particle, just heading the other way through the temporal dimension. The annihilation isn't a death, it's a change of direction. But if matter can turn around in time, what does that mean for the light that connects it? The squiggly line in the middle? Does the photon have an arrow? This is where your brain might start to hurt, because the photon is the one thing in the universe that breaks all the rules of time. Let's go back to that diagram for a second. Two electrons meet. One sends a photon to the other. They repel. In our normal world, we say electron A sends a photon to electron B. Cause, effect. But Feynman's diagrams don't care about your feeling of time. They care about symmetry. Look at the squiggly line representing the photon. It connects the two electrons. Does it have an arrow? No. Photons don't have arrows. They don't distinguish between past and future. To a photon, the journey from A to B takes 0 time, because at the speed of light, time stops. Literally. If you were a photon leaving the sun, the moment you leave the surface and the moment you hit the earth are the same moment to you. To us, it takes 8 minutes. To the photon, it takes 0 seconds. So, if time doesn't exist for light, then forward and backward become meaningless for light. Now apply this to the electron. The electron does experience time. It has mass. It moves slower than light. But when it interacts with light, when it absorbs or emits a photon, it can change direction in time. Remember the annihilation? Electron plus positron equals energy. In a Feynman diagram, you see an electron moving forward in time. It hits a photon. Suddenly, the arrow flips. It starts moving backward in time. To us, watching from the outside, we see a positron moving forward in time towards the collision point. The collision point is where the forward electron meets the backward electron, which looks like a positron. Bam! They vanish into light. But to the electron itself, it just kept going. It didn't die. It just turned around in the time dimension. This is the big aha moment. Antimatter isn't some weird alien substance. It's just normal matter moving the wrong way through time. The positron is the electron traveling backward from the future. Think about what this means for reality. Every single positron you've ever heard of, in PET scans at hospitals, in particle colliders, in cosmic rays, is just an electron traveling backward in time. It means the universe is filled with particles moving in both directions through the temporal dimension. We are so used to thinking of time as a river flowing one way, but quantum mechanics suggests it might be more like a two-way street. Traffic is heavy in the forward lane, matter, but there are cars driving in the backward lane too, antimatter. And occasionally a car does a U-turn, annihilation or pair production. If this is true, then every time an electron and positron annihilate, it's not the end of the story, it's just a corner. The particle turns around and heads back into the past. But if particles can travel back in time, why don't we see time travelers? Why can't we send messages to yesterday? Well, because there's a catch, a big one, and it has to do with how much antimatter there actually is. Let's rebrand antimatter for a second. Forget antimatter. Forget sci-fi fuel. Forget explosion hazards. Call it what it really is, time-reversed matter. Every positron is an electron traveling backward in time. Every antiproton is a proton traveling backward in time. If you meet an antimatter version of yourself, don't shake hands. You'll both turn into pure energy. But think about what that handshake means. From your perspective, moving forward in time, you see your anti-self moving forward to meet you. From the universe's perspective, in 4D space-time, you are just one long, squiggly world line that turns around in time at the moment of the handshake. You were moving forward. Then you hit a massive energy event, the handshake, and you bounced off backward into the past as antimatter. Wait, that sounds insane, but look at the math again. In a Feynman diagram, you can rotate the whole picture. Take an electron emitting a photon, rotate it 90 degrees. Now it looks like an electron and a positron appearing out of nowhere, pair production. Rotate it another 90 degrees. Now it looks like an electron and a positron disappearing into nothing, annihilation. Rotate it again. Now it looks like a positron absorbing a photon. It's the same event, just looked at from different angles in space and time. To a particle physicist, these are all the same process. Emission equals absorption equals pair production equals annihilation. They are just different ways of slicing a 4D object called a world line. A world line is the path an object takes through space-time. Most of us think world lines go straight from past to future, like a ruler. But Feynman showed us that world lines can zigzag, they can loop, they can knot. When an electron zigs backward in time, we call it a positron. When it zags forward again, we call it an electron again. So antimatter isn't a different kind of stuff. It's the same stuff, just pointed in a different direction through the temporal dimension. It's like seeing a car driving down the highway. That's an electron. Then you see the same car driving back up the highway in reverse gear. That's a positron. Same car, different direction. And this leads to the most mind-bending question of all. If electrons can zigzag back and forth through time, how many electrons are there really? Are there trillions? Or is there just one? Before we get to that, and trust me, it's wild, we need to look at the photon again. Because while matter zigzags, light does something even stranger. It doesn't even know what time is. If matter can turn around in time, what about light? Remember those squiggly lines in the Feynman diagrams? The ones connecting the electron to the other electron? That's a photon. Now here is the secret life of a photon. A photon doesn't have a mass. It has zero mass. According to Einstein's special relativity, anything with zero mass travels at the speed of light. And at the speed of light, time dilation becomes infinite. Time stops. For a photon, the moment it is created in the heart of a star and the moment it hits your retina a million years later are the exact same moment. To a photon, the entire history of the universe happens in an instant. It is born, it dies, all at once. So asking, is light moving forward or backward in time, is a trick question. To a photon, there is no forward or backward. There is only now. It connects 2 points in space-time instantly. But here is where it gets weird for us. We aren't photons. We have mass. We experience time. So when we look at light, We see it moving. We see it take 8 minutes from the sun. We see it take 4 years from Alpha Centauri. But in the math of quantum electrodynamics, QED, the photon doesn't care about the direction of time. It can be emitted by an electron in the future and absorbed by an electron in the past, or it can be emitted in the past and absorbed in the future. The equations are symmetric. They don't distinguish. This means that every single interaction involving light is fundamentally time reversible. If you videotape an electron absorbing a photon and play it backwards, you see an electron emitting a photon. Both processes are physically valid. Both happen all the time. So light is the bridge. It's the timeless connector between events. It stitches the past to the future and the future to the past in a seamless web of causality. But if light is timeless and matter can zigzag through time, then what is the universe actually made of? Is it a swarm of trillions of particles? Or is it something far simpler? Something so simple it sounds like a joke. But Richard Feynman wasn't joking when he called John Wheeler one night with a crazy idea. An idea that explains why every single electron in the universe looks exactly the same. It's 1940. Richard Feynman is sitting in his office at Princeton. The phone rings. It's his mentor, John Wheeler. Wheeler says, "Feynman, I know why all electrons have the same charge and the same mass." Feynman asks, "Why?" Wheeler replies, "Because they are all the same electron." Wait, what? Imagine a single piece of string, just one, but it's infinitely long. Now, imagine weaving that string back and forth through time, up, down, like a giant loom. If you take a slice of time, imagine cutting across the loom with a ruler, you would see thousands of little points where the string passes through the slice. Some points are the string going up, forward in time. Those are electrons. Some points are the string going down, backward in time. Those are positrons. But they are all just cross-sections of the same single string. This is the one-electron universe theory. It suggests that there is only one electron in the entire cosmos, just one, bouncing back and forth from the Big Bang to the Big Crunch, over and over again, weaving the fabric of reality. Every electron in your body, the same electron as the one in a star a billion light years away. The same one in your coffee cup. The same one in a dinosaur's tooth. It's just visiting different places at different times on its eternal journey. This explains why every electron is identical, why they all have exactly the same mass, charge, and spin. Because they are literally the same object. And every positron? Just that same electron on its return trip from the future. Now, Feynman laughed at this. He pointed out a flaw. If this were true, there should be an equal number of electrons and positrons in the universe. For every up stitch, there must be a down stitch. But we see way more matter than antimatter. Where are all the positrons hiding? Wheeler had a clever answer. Maybe they are hiding in protons, which turned out to be wrong, but still clever. Even though the theory has holes, the core idea stuck. Particles are not separate marbles. They are excitations in a field, and those fields don't care about time. But if electrons can bounce back and forth through time, why can't we? Why are we stuck moving forward? Why don't we see people walking backward down the street? Or uneating sandwiches? The answer lies in the sheer number of particles involved. It's the difference between a single coin flip and a billion coin flips. So here we are. Electrons can go backward in time. Positrons can loop through the past. Photons don't even know what time is. So why are you stuck? Why is your life a one-way street? Why can't you remember tomorrow's lottery numbers? The answer is entropy. But not just the messy room kind. Think about a single coin. Flip it, heads or tails, 50-50. It's reversible. Now flip a billion coins, all at once. What are the odds that all of them land heads? 0. Practically impossible. You are made of roughly 7 times 10 times 27 atoms. That's a 7 with 27 zeros. Each atom is following quantum rules. Each atom could technically move backward in time for a split second. But for you, the whole person, to move backward in time, every single one of those 7 by 10 by 27 atoms would have to coordinate perfectly. They would all have to reverse their momentum at the exact same instant. It's like trying to get 1 billion people to jump at the exact same millisecond. It's not forbidden by physics, it's just statistically impossible. This is the bridge between the quantum world and our world. Down there, time is a two-way street. Up here, it's a rushing river. We are emergent phenomena. We are patterns built on top of the chaos. And because we are patterns, we rely on the flow of entropy to exist, to think, to remember. Your brain records memories by increasing entropy, by burning energy, by creating heat. That process requires time to move forward. So even if the atoms inside your neurons are doing a little temporal dance, the pattern of you is locked in the flow. But wait, if we can't physically travel back in time, can we see back in time? Yes, we do it every night. When you look at the stars, you are looking into the past. But Feynman's diagram suggests something even deeper. They suggest that the future is already written in the paths of particles, that the now is just a slice of a 4D block universe. And if that's true, then maybe, just maybe, the future is already here. We just haven't caught up to it yet. Let's end where we began, with that coffee cup smashing on the floor. You see the shards, you feel the regret, you accept the arrow of time. But remember the trick. Remember the electrons dancing in the ceramic, the photons bouncing off the liquid. Every single one of those particles is weaving a path through time that doesn't care about forward or backward. They are following the deep symmetry of the universe. And in that symmetry, there is a hidden truth. That antimatter isn't just exotic fuel for starships. It is the universe's way of balancing the books. It is matter returning from the future. It is a reminder that what we perceive as a straight line from birth to death is actually a complex knot in space-time. A knot where cause and effect can blur, where particles can be their own grandparents. So the next time you look in the mirror, remember this. You are made of time travelers. You are built from light that has no time, from electrons that might be the same single electron visiting you over and over again. And just because you can't remember tomorrow doesn't mean the atoms inside you haven't been there. Maybe they have. Maybe they are just waiting for you to catch up. The universe isn't just a machine moving forward. It's a tapestry woven in all directions at once. And we are just the patterns trying to make sense of the threads. Physics tells us the rules, but it doesn't tell us why. Why does time flow for us? Why does it feel so real? Perhaps that's the one secret light will never reveal. Or perhaps it already has, and we just haven't learned to read the message backwards yet. Think about that. If you enjoyed this journey into the impossible, hit that subscribe button. It helps the algorithm find more curious minds like yours. And until next time, keep looking up.